Hello and welcome back. So today we're going to be looking at lecture 3 in our electronics module. And here we're going to be crossing the bridge from analog to digital, which is the transition that makes modern instrumentation possible. So far in this module, we've traced the analog signal from the transducer through op-amp and filter. And today we're going to take that clean analog voltage and turn it into digital numbers your computer actually uses. And so then we'll also look at the reverse reaction, so how a computer controls the instrument using digital to analog conversion. So we have 6 objectives. You can see them here. Effectively, we're going to be just trying to understand how the digital to analog systems interface and work. So this is part of our roadmap for today. We'll recap our previous lecture. We'll look at the difference between analog and digital. We'll look at some number systems, logic gates, the ADC, the DAC, and so on. And we'll look at some worked examples as we always do. So last time we built tools for analog signal conditioning, op-amps which amplify by negative feedback. But we had 2 golden rules that no input current and V plus equals V minus. We learned 5 configurations: inverting, non-inverting, voltage follower, trans impedance, and summing. And we learned about RC filters with the cutoff frequency formula FC equals 1 over 2 pi RC. In today's lecture, we're going to be connecting to this as well, and we're going to be looking at how the op-amp and filter give us a clean analog signal. But the computer can't work with the analog, it needs digital numbers. The bridge is the ADC, and we'll spend most of today understanding it. We'll also look at the return bridge, the DAC, that lets the computer control the instrument. So here we have the analog to digital signal comparison. So on the left, we have an analog signal. It's continuous in time. It has value at every instant, and it's continuous in amplitude. You can take any value within its range. In principle, analog signals have infinite resolution. Real-world physical and chemical phenomena produce analog signals naturally. But the analog has downsides. Every time you copy or transmit an analog signal, noise accumulates. That's why old photocopies of photocopies get fuzzy, or why old cassette tapes recordings degrade. On the right is a digital signal. It's discrete in both time and amplitude. The signal is sampled at specific moments, and each sample is rounded to one of a finite number of levels. The red dots are the samples. The step-like curve shows the digital approximation. Digital has enormous advantages. You can store it indefinitely without degradation. You can transmit it across the globe losslessly. You can apply sophisticated math, so Fourier transforms, averaging, filtering, etc., effortlessly. You can copy a digital file 1,000,000 times, it's identical to the original. That's why every modern instrument digitizes as early as possible in the signal chain. Number systems then. So we have different number systems. Computers think in binary. They are fundamentally binary. Their transistors have 2 stable states, either on or off, 1 or 0. So all information inside a computer is binary. We humans find binary cumbersome, so we use decimal. And engineers often use hexadecimal as a compact shorthand for binary. The place value concept should be familiar from elementary math. Decimal 347 is 3 times 10 squared plus 4 times 10 plus 7. Binary 1011 is 1 times 8 plus 0 times 4 plus 1 times 2 plus 1, which equals 11 in decimal. Hexadecimal 2F is 2 times 16 plus 15, which equals 47. The key insight is at the bottom. With n bits, you can represent 2 to the n distinct values. 1 bit gives you 2 values. 8-bit gives you 256. 16-bit gives you 65,536. This geometric growth is why even small increases in bit depth dramatically improve resolution. Here we have a table which shows the decimal 0 through 15 in all 3 systems. You can probably notice a pattern. 4 bits give you exactly 16 values, which is exactly 1 hex digit. This is why hex is so convenient. 2 hex digits is 8 bits or 1 byte. You'll see hex everywhere in an instrument data files, raw data dumps, instrument firmware, register addresses. When you see a string like AFC4E3E, That's 3 bytes of binary data expressed compactly in hex. The example binary 10101111 is AF in hex, which is 175 in decimal. We can practice this conversion because it'll come up in the practice problems. Here's the vocabulary. A bit is 1 binary digit. A nibble is 4 bits or 1 hex digit. A byte is 8 bits, a fundamental unit of computer storage. A word is 16, 32, or 64 bits, depending on the processor. The table on the left shows distinct value counts for different bit depths. Look at the row for 12 bits, 4,096 levels; for 16 bits, 65,536; for 24 bits, over 16 million. Each additional bit doubles the number of levels. In analytical instruments, the ADC bit depth directly sets the measurement resolution. 8-bit ADCs are rarely sufficient. Only 256 levels is coarse. 12-bit is common for basic instruments. 16-bit is standard for most spectrophotometers. 24-bit is used in high-end FTIR and NMR, where you need the dynamic range to measure a weak signal on top of a strong background. So why would we want to pay for a 24-bit ADC instead of a 16-bit? What's that extra resolution worth? So logic gates are the building blocks that we're going to be using. So digital circuits are built from logic gates. These are physical components that implement Boolean operations on one or more inputs. The 5 most important gates from left to right: and produces 1 only when both inputs are 1, or produces 1 when either input is 1. Not inverts its single input. NAND is not and, the opposite of and, nor is not or, the opposite of or. There is also XOR and XNOR, exclusive or exclusive NOR, which you can see in the truth table at the bottom. Here's a pretty fun fact. NAND and NOR are what are called universal gates. You can build any digital circuit using only NAND gates or only NOR gates. That's why semiconductor manufacturers often fabricate chips with NAND gates. It's efficient to mass produce just one type. The big picture in the alert block is that every digital operation, addition, image processing, and machine learning, reduces to combinations of these simple gates. The chip controlling your UV vis contains billions of transistors implementing billions of gate operations per second, all built from these basic logic functions. Digital circuits come in 2 flavors. Combinational logic means the output depends only on the current inputs, no memory. Pure input to output mapping through gates. Examples are adders, multiplexers, decoders, and so on. Sequential logic means the output depends on current inputs and past history. It has memory. Implemented with flip-flops. It needs a clock to advance from one state to the next. Some examples are counters that count clock pulses, registers that store data, and state machines that orchestrate instrument behavior. In your instruments, the ADC's comparator array is combinational. It decides the digital code based purely on the current input voltage. But the chromatography data system is sequential. It counts timing pulses, knows which step of the method you're on, and remembers the calibration coefficients between injections. But what does an ADC actually do? The ADC, or the analog to digital conversion, takes an analog voltage in and produces a binary number out. That binary number encodes the voltage as one of 2 to the n discrete levels. It does 2 operations: sampling and quantization. Sampling means taking a measurement at a specific moment in time. Quantization means rounding the measured voltage to the nearest allowed level. The specifications you care about are the resolution n, the number of bits, sampling rate f sub s, how many samples per second, input range, the voltage window the ADC accepts, and accuracy, how close the output is to the true value. The fundamental trade-off here is at the bottom. We've got more bits give better resolution, but is more expensive and often slower. Higher sampling rate gives better time resolution with more data to store. Instrument designers constantly have to balance these. So with regards to quantization, we're basically asking how many levels, which is going to be linked to the step size, which is often called LSB or least significant bit, right? So it's explained here as delta V is range divided by 2 to the n. Delta V is equal to V range over 2 to the power n. That's the smallest voltage change the ADC can distinguish. The table below shows concrete numbers for different resolutions and input ranges. For a 5-volt range, an 8-bit ADC has steps of 19.5 millivolts, which is pretty close. A 12-bit ADC gets to 1.22 millivolts. A 16-bit ADC gets to 76 microvolts, a 24-bit ADC to 0.3 microvolts, with each jump in resolution being pretty dramatic. The rounding that happens during quantization introduces an error of up to plus or minus half a step, which is called quantization noise, and it sets the fundamental noise floor of any digital measurement. The formula SNR max equals 6.02 n plus 1.76 dB tells us that every bit buys you about 6 dB of dynamic range. That's roughly a factor of 2 in amplitude ratio per bit. So we can ask if we go from 12-bit to 16-bit, how many bits have we added? How much SNR improvement? So if we've increased from 12 to 16, we've gone up by 4 bits, which is somewhere around about 24 dB. So now we're on to sampling and the Nyquist theorem. So now the Nyquist-Shannon sampling theorem is one of the most important results in signal processing, and it has practical consequences for every instrument design. The theorem says to faithfully represent a signal containing frequencies up to Fmax, you must sample at a rate of at least 2 times Fmax. The sampling rate must be at least twice the highest frequency in the signal. If you violate this, i.e. if your sample is too slow, then you get aliasing. If you sample too slowly, you get aliasing, which is high frequency content folds back and appears as lower frequencies in your digital data. Now here's the critical part. Once the data is digitized, you cannot distinguish the aliased signal from a real low frequency signal. The damage has already been done. Look at the plot on the right. The blue solid curve is a real 3 Hz signal. We sample it at only 3.33 Hz, which is too slow. The red dots are our samples. If you connect the dots, you get the dashed red curve, which looks like a 0.33 Hz signal, which is total fabrication. The high frequency has been aliased down. The only defense against aliasing is an analog low-pass filter before the ADC, the anti-aliasing. That removes any content above Fs over 2 before digitization. That's the exact low-pass filter we designed last lecture. So there are 4 common ADC architectures, each with different speed resolution trade-offs. An SAR, which is a successive approximation, is the workhorse. It uses a binary search to find the input voltage 1 bit at a time. Medium speed, 8 to 16 bits of resolution, most common in embedded systems and general purpose instruments. Flash ADCs use parallel comparators, one per quantization level, which makes them extremely fast. They convert in a single clock cycle. But they're limited to about 10 bits because you need 10 to the 24 or 1024 comparators for 10 bits. And that can get expensive fast. Used in oscilloscopes and high-speed transient detection. The next one then is a sigma delta ADC, which are my personal favorite. They oversample massively, hundreds or thousands of samples per final output sample, and then digitally filter. The clever trick here is called noise sampling. The quantization noise gets pushed to high frequencies where the digital filter removes it. This gives incredible resolution of around about 24 bits or more, at the cost of speed, which is primarily used in FTIR and NMR. Then the last one is the dual slope integrating ADC, which are pretty slow but extremely accurate. and they naturally reject power line interference. You can find them in digital multimeters and pH meters. So how about the opposite, the DAC, the digital to analog conversion? So the DAC does the opposite of the ADC. Digital number in, analog voltage out. The output is V ref times D over 2 to the n, where D is the decimal value of the digital input. The example is shown here and how we do that calculation. An 8-bit DAC with a 5-volt reference, feed the binary code 10110101, which equals 181. Outputs 5 times 181 over 256, which equals 3.54 volts, which gives us pretty simple linear scaling. There are several DAC architectures. The R-2R ladder is elegant. It uses only 2 resistor values regardless of resolution and is easy to match precisely. Weighted resistor DACs use a different resistor per bit, which becomes hard to match for high resolutions. String DACs use a long chain of matched resistors and tap off at different points. They're guaranteed monotonic, meaning the output always increases as input increases, which is important for control applications. And sigma delta DACs are the mirror image of sigma delta ADCs. So where can we see DACs in analytical instruments? So they show up pretty much everywhere the computer needs to control something analog. Monochromator stepper motors are driven by DAC-generated voltages. Lamp intensity is maintained by a DAC-controlled current driver. Auto samplers use DACs to position syringes. GC oven temperatures and HPLC column heaters have their set points programmed through DACs. And even the ADC's own reference voltage might come from a DAC. The block on the right shows how ADC and DAC work together in closed loop control. The ADC measures the current state, say the column temperature. The computer compares to the set point. The DAC adjusts the heater power. The cycle repeats hundreds of times per second, and that's how a GC oven holds its temperature program to plus or minus 0.1 degrees Celsius. The key point here is that the ADC and DAC are the 2 bridges between the analog world and the digital computer. Every automated instrument will make use of both. So that finishes our theory. So now on to some of our worked examples. So we have a few of these. So the first one is going to be an ADC specification for a UV-Vis spectrophotometer. So here we have a scenario where you're specifying an ADC for a new UV-Vis spectrometer. The transimpedance amplifier from our previous lecture outputs 0 to 5 volts. The smallest meaningful change is 0.0001 absorbance units, which corresponds to 0.5 millivolts at the detector output. The instrument scans 200 to 800 nanometers at 1 nanometer per second with 1 nanometer resolution. Okay, so we move on to part A, which is the minimum resolution. We need a step size no larger than 0.5 millivolts across a 5-volt range. That means 2 to the n must be at least 5 divided by 0.5 millivolts, which equals 10,000. Since 2 to the 13 is 8,192 and 2 to the 14 is 16,384, we're going to need at least 14 bits. The nearest standard choice is 16-bit. Okay, so that gives us the first part. So the second part then is the actual step size will be 16 bits. Delta V equals 5 divided by 65,536, which gives 76.3 microvolts. That's about 6.5 times finer than our 0.5 millivolt requirement, which is perfectly good and comfortable headroom. Part C then, quantization SNR. So 6.02 times 16 plus 1.76 equals 98.1 decibel. That's a dynamic range of about 80,000 to 1. Excellent for absorbance measurements up to 4A. Part D, minimum sampling rate. The signal changes at 1 hertz. Nyquist requires 2 hertz minimum. In practice, we'd oversample at 10 to 100 hertz, an average, which also improves the SNR. So our conclusion here is 16-bit ADC sampling at 10 hertz or higher with a 4 hertz anti-aliasing filter satisfies all of our requirements. This is exactly the specification you'd find in modern commercial UV-Vis instruments. Our second worked example then is shown here. So this is looking at aliasing and Nyquist and GCMS data acquisition. So a GCMS scans mass to charge from 50 to 500 at 5 scans per second, and an engineer proposes sampling the detector at 5 kilohertz. There is no anti-aliasing filter yet. There's also a 50 hertz power line interference on the detector signal. Okay, pardon. What's the highest frequency in the useful signal? Each scan takes 200 milliseconds, covering 450 mass to charge MZ units. Peak widths are about 1 m over z. So one peak crosses the detector in roughly 0.44 milliseconds. That gives a signal bandwidth of about 2 kilohertz. Part B then, is 8 kilohertz sampling adequate? Nyquist requires at least 4 kilohertz. At 8 kilohertz, we oversample by 2 times, adequate for the signal. Part C, what happens to the 50 hertz power line interference? 50 hertz is far below 2F, or far below, sorry, Fs over 2, which is 4 kilohertz. So 50 hertz does not alias. It appears in the digital data at 50 hertz and can be removed by digital filtering after acquisition, which is good. But part D, what if there's an RF interference at 10 kilohertz? Now we have a problem. 10 kilohertz is above the Nyquist frequency of 4 kilohertz. It aliases to 10,000 minus 8,000, which is equal to 2 kilohertz, right in the middle of our useful signal band. After digitization, that 2 kilohertz artifact is indistinguishable from real peaks, okay? So this is important to check. So this is a silent failure. The data will look normal, but contains fabricated peaks. And so there's no way to diagnose it from the digital data alone, okay? So what is the fix? The fix is to install an analog low-pass filter with a cutoff around 3 kilohertz before the ADC. That preserves the 2 kilohertz signal content, but attenuates anything that could alias. This kind of mistake is one of the most common hidden sources of bad data in instrument design. We'll always ask, where is the anti-aliasing filter whenever you're checking the diagrams for your instrument? Worked example number 3. So this is our third and final example for lecture 3. So a UV-Vis uses a 12-bit DAC with a 3.3 volt reference to control the deuterium lamp current. The current driver is linear, 10 milliamps per volt of DAC output, giving 0 to 330 milliamps. So part A, resolution in the lamp current, okay? So the DAC voltage step is 3.3 divided by 4096, which equals 0.806 millivolts. The current step is 0.86 or 0.806 times 10 to the minus 3 times 100, which gives 80.6 microamps. Part B, what DAC code achieves 200 milliamps? So the first thing is that the required DAC voltage is 200 over 100, which equals 2.0 volts. Then the DAC code D equals 2.0 times 4096 divided by 3.3, which gives 2,483. In binary, that's 1001, 1011, 0011. In hex, 93. Part C then, is the 12-bit resolution sufficient? If we need to control lamp current to plus or minus 0.1 milliamps, that's 0.05% precision. The 80.6 microamp step size is comfortably below this, so 12 bits is fine. For research grade instruments needing tighter control, a 16-bit DAC gives a 5 microamp resolution. Key takeaway here is that the DAC specs directly determine how precisely the computer can control the instrument. We want to match the DAC resolution to the application. More bits cost more, but this isn't always necessary. So here are our key takeaways, and make sure that you keep the connections going. And that there are connections to this lecture, the previous lecture, and the future lecture. So coming up next, we'll talk about signals and noise. And so after that, we have some practice problems that you can please attempt. Solutions will be, of course, posted. And then, of course, you can always include some questions. Okay, so feel free to ask me some questions, and we'll be sure to answer.